Pigeons are the birds we probably come across most in our daily lives. These tiny creatures may not attract many people's attention, but when we examine them closely, they are a miracle of creation. In order to see the truth of this, let us consider how a pigeon takes off from the ground and witness a flawless piece of engineering design. First of all, the pigeon jumps up in the air. It then raises its wings at the moment its feet leave the ground and pushes the air behind it with all its strength. It then leads slightly forward. It has now risen high enough in the air to be able to move forward. Larger birds than pigeons cannot perform this difficult movement more than twice. Really large birds, such as the albatross, cannot do it at all, although they possess other techniques allowing them to leave the ground. One example is running along at ever-increasing speed. That is a technique also used by us in aeroplanes. The most tiring part of flight for most birds is the moment of takeoff. Once that has been achieved, a bird can easily glide in the air. So, what is it that enables a bird to stay up in the air once takeoff has been achieved? The answer lies in the flawless engineering design in the wing. The back of the wing curls slightly downwards. Air passing under the wing strikes that part and exerts a force on it. That lifts the bird upwards. Air passing over the wing, on the other hand, is deflected upwards by the front of the wing, and air pressure on top of the wing is reduced. That also pulls the bird upwards. If there is sufficient current, the attractive force above the wing and the lifting power from underneath are sufficient to keep the bird in the air. It is this factor that allows the albatross to stay aloft for hours without once flapping its wings, just making use of the rising currents of air. Other birds create the necessary current underneath their wings themselves, flapping their wings to do so. This bird is literally rowing in the air. It pulls half of its wing in towards its body as it raises it, thus reducing friction. It then fully opens its wings as it lowers them again. The feathers intermingle with every movement. Thus, although the wing changes shape at all time, the underside of the wing stays completely smooth. Birds' feathers and wing shapes are aerodynamically quite perfect. Even though this duck flies at speeds approaching 70 kilometers an hour, it looks as if it's just gliding slowly through the air, thanks to its perfect aerodynamic structure. Different bird wings have always been used in aeroplane design. Some wings are short and sturdy for frequent maneuvering. Others are long and wide in order to be able to fly at high altitudes. Still others are long and narrow for gliding in the air. Allah has created the perfect flight system in the body of every bird in line with its own requirements. Some birds stay in the air for months, eating, drinking, and sleeping there. Hawks dive onto their prey at up to 300 kilometers an hour. Eagles fly to demonstrate their power, not just to find food. This dogfight between these two eagles is not actually a fight at all, but rather a test of courage. The first to release its talons before falling to earth will lose. This wonderful spectacle of flight thus emerges. All flights have to end with landing. A safe descent is therefore just as important as takeoff. Birds are expert at this and use their wings as brakes. This puffin can remain suspended in the air thanks to the air currents around it, and uses that same ability to land again. A moment's lack of concentration could have terrible consequences. Swans, some of the largest birds on Earth, land on water, just like a seaplane, and use their feet as brakes. A vulture uses the most accurately controlled flight and spot-on geometric calculation to make a safe landing in its nest on the edge of a cliff. It first aims at a point below its nest and makes a rapid descent, and then suddenly turns upwards, using the air as a brake, and its speed drops to zero just as it nears the nest.